Right. Today we are going to talk about quadratic inequalities in one variable, specifically solving or solutions to quadratic inequalities in one variable. And I'll just jump right in with a few examples of working through these things. Um, so your first example is example 1 from page 478 of your textbook. And you're asked to solve x squared minus 2x minus 3 less than or equal to 0. And much like the systems of linear inequalities, there's not a graph is not a bad way to go with these things. So I'm going to jump right to a graph. There's a few different ways to do this, and I mentioned all three in this example, but I tend to stick with the graphs more for these quadratic inequalities. So we'll start there with graphing. So in graphing, I'm going to graph the quadratic statement, y equals x squared minus 2x minus 3. And all I really care about, there's two parts I care about, where the zeros are, where the x-intercepts are, and whether this quadratic opens upward or downward. That's all I really need to know in order to solve this quadratic inequality. Now this one happens to factor quite nicely. It happens to factor into x minus 3 times x plus 1. So that means it has x-intercepts at x equals negative 1 and positive 3. And if I make myself a quick sketch of a graph on this, I know that I've got an x-intercept at negative 1 and at positive 3, and the graph opens upward. If I want to get a little fancier, I know the y-intercept is at negative 3 as well. I'm not too worried about that. Okay, so here's my quadratic. Y equals this. So every point on this line, my y value is equal to this quadratic statement. But I also know I want this quadratic statement to be less than or equal to 0. So if I put these two things together, what I'm looking on this graph is where is y less than or equal to 0, or where are my y values negative. And on this line, my y values are negative in all of these places. So in all of this area, my quadratic statement is less than or equal to 0. So I just need to find a way to state that in terms of x. And those are going to be x values between negative 1 and positive 3. So if I wrote that out, I would say x squared minus 2x minus 3 is less than or equal to 0 for x values between negative 1 and 3 inclusive, including the negative 1 and the 3 because they're part of the solution. Now, as I've said before, math people, we're a little on the lazy side. I do not want to write this whole statement out each and every time, so I've got a couple of different ways that I can state this. One is with a domain type statement. I could also say that this is true for x, where x is between negative 1 and 3. That would be another way to state the solution. But I'm going to mention something here called interval notation, which I will tend to use a bit more and crops up a bit more and more further on you go with math. And for that, I would say that x is a part of the set from negative 1 to 3. And that would be a domain solution. Note here, square brackets include the endpoints. Okay, I mentioned there were going to be three ways that we could show to solve this. Graphing was one of them. Two involves what we call roots and test points. And it's kind of similar to what we did above, just we don't make the graph and we try a couple of points. So we know from before our zeros of x squared minus 2x minus 3 are at x equals negative 1 and 3. So if these are where the zeros of this statement are, then these are the only places the function can go from positive to negative. If my function works out to be positive 2, the only way I can get that to a negative value is to go through one of these x values. It's the only way to change it from positive to negative or vice versa. So what I do, or I check a few points around these values. So let's say I check something below negative 1. Check x equals, doesn't really matter as long as it's less than negative 1. So I'm going to say negative 2. Negative 2 squared minus 2 times negative 2 minus 3 is equal to 4 plus 4 is 8 minus 3 is 5. 5. Or positive. And what that means is that for everything less than negative 1, this is going to turn out to be positive. The only way it could change from positive to negative is to go through a 0, and the only 0 is at x equals negative 1. At least the only one on that side of things. So then I will check a value between the two. Between negative 1 and 3, 0 works quite nicely. 0 squared minus 2 times 0 minus 3 equals negative 3, or negative, which means everywhere between negative 1 and 3, if one value made the whole thing negative, then anything between negative 1 and 3 will make the whole thing negative. And then finally, I check a number bigger than 3. So let's say 4. 4 squared minus 2 times 4 minus 3. That's 16 minus 8 is 8 minus 3 is 5, or positive. Now, because we want x squared minus 2x minus 3 to be less than or equal to 0, then this is the outcome that we want. Or in other words, x has to be between negative 1 and 3 inclusive. The next, again, is similar and involves a case analysis. And this one I really don't use a whole lot, other than occasionally I might kind of fly through it in my head if I want to get a quick number and things were set up nicely. So, remember, we are solving x squared minus 2x minus 3 is less than or equal to 0, but I will show it as the factors x minus 3 times x plus 1 have to be less than or equal to 0. And then we just sort of think our way through what happens for different values of x. So, for instance, if x is going to be less than 3, then this number is negative. This number will be positive or negative depending on how much less, which would tell us whether this is positive or negative. So, we check the same sort of ranges. Less than negative 1. That would make x plus 1 negative, and x minus 3 negative, and a negative times a negative is positive. if I go between -1 and +3, then x plus 1 is positive, x minus 3 is negative. Therefore, overall, I have a positive times a negative, and the whole thing is negative. And lastly, greater than 3, x plus 1 is positive, and x minus 3 is positive. Therefore, overall, that's a word, it is positive. The overall negative is the only one I'm interested in this case. That leads me to that same solution. So any of these will work. I tend to find myself graphing more often than not, because it is a quadratic statement. We have graphed a fair number of those, and all I really care about are the location of the x-intercepts and whether it opens upward or downward. So I will tend to go that way more often than not. I'll do a couple more examples. This next is example 2 off page 480. And we are asked to solve negative x squared plus x plus 12 less than 0. So I won't run through each different way in this case, so I will look at the graphing solution. So if I graphed y equals negative x squared plus x plus 12, I'm going to factor my negative out front. And then this thing does nicely break down into two factors, positive 3 and negative 4. And that's enough for me to sketch a rough graph of this thing. I'm probably not going to get the y-intercept on this thing nicely unless I change my scale, which I could do, I guess. Go up by 1s here, and I'll go up by 4s here. So I know I've got x-intercepts at positive 3 and negative 4. I know I've got a y-intercept at positive 12, and because of the negative sign, I know this thing opens downward. So my graph would look something like this. So, with my graph, then I can think about the inequality. I am interested in where this statement is less than 0 or in where y is less than 0. My y values are negative here and here. So my solution to this inequality will be true when x is greater than 3 or less than negative 4, but not including 3 and negative 4, because there's no equals part of this inequality. So how would I write that out in interval notation? X is in the set, from negative infinity to negative 4, joined with the set from 3 to infinity. And this is how I will tend to write these solutions out, although I will show you how your book would write them out in a second here as well. So the infinities let you go on forever off in either direction. The little U-shaped thing here in the middle means a union of sets. So your solution is the union of the set of numbers from negative 8 up to negative 4 and from 3 to infinity. Notice that all my brackets are round in this case, and the round brackets mean we're not including the endpoints. I can't include infinity anyway because it's infinity, but I'm also not including the negative 4 or the 3. Round brackets don't include endpoints. Your textbook answer would look something along the lines of x, where x is less than negative 4, or x greater than 3, x in the reals. That would be your textbook solution. Although again, I tend to write it out more this way. I would take either answer though, so whichever one you're more comfortable with. Lastly, I'll look at one that doesn't factor quite so nicely, and you've got to rearrange a little bit. So this is example 3 from page 482, where you are looking to solve 2x squared minus 7x is greater than 12. So I'm going to make that look like a quadratic a bit more first, or a quadratic we're used to dealing with. 2x squared minus 7x minus 12 is greater than 0, which means I want to try to graph 2x squared minus 7x minus 12. Y equals that. This does not factor nicely, so I end up at the quadratic formula. Zeros at x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's at 7 plus or minus the square root of 7 squared minus 4 times 2 times negative 12 all over 2 times 2. Or if I simplify that a little bit, 7 plus or minus root 49, this is going to end up being positive, 48, 2 of those are 96, 96 plus 49, 96 plus 49 would be 145 over 4. So your exact roots of this thing are 7 plus root 145 over 4 and 7 minus root 145 over 4. But in the interests of graphing these, I will state their decimal approximations as 4.8 and negative 1.3. So then I can make a quick graph of this. X and Y, and I'll do the same thing and go up by 1s in the X and up by 4s in the Y. So my roots are at approximately negative 1.3. And positive 4.8. I also have a y-intercept at negative 12. And I'm looking to, well, my quadratic opens upward. So it's going to look something like this. And I'm interested in where this statement is greater than 0 or where it's positive. Now I do want to stress I'm coming back to this statement and not this one, because this is what I've graphed. So that's the comparison I need to make. Now, these inequalities aren't exactly the same, but since we followed the rules of algebra, solving this one gives you the same solution as solving this one. So, where's this quadratic greater than 0? Where's the y value is positive? That's in this area and this area. So my solution would be x is in the set from negative infinity up to negative 1.3, joined with the set from 4.8 to infinity. And that would be my solution. And I just want to stress one thing. If this had been 2x squared minus 7x minus 12 greater than or equal to 0, then my solution would have been a round bracket on the infinities, but a square bracket on the non-infinite endpoints. Okay, that is a bit on solving quadratic inequalities. There'll be a few practice questions for you to try on the Google Classroom site, and thank you for your time.